So I guess I'm going to try to do it using Notepad. Need to set up the camera so that I can toggle between the two, point it at the screen. But from this angle, it would look pretty stupid. Maybe not that bad. Okay, so we're going to hop into our little binary car, our bit car. What is binary? It's a counting system where there's only two digits, 0 and 1. We're going to call that base 2. We're also going to call it binary. And we're going to indicate that it's base 2 sometimes by putting a parentheses 2 after it. So here's a number in base 2, right? You can have all zeros in base 2. You can have all ones in base 2. Now normally you're not going to only have 4 bits. A bit is a binary digit, right? Which is equal to 1, 0, or 1. So here's 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Here's another 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Like that. We'll get to our bit car in a second. That's binary. Now decimal is what we count in. We with our 10 fingers. You know, if we had been created with 16 fingers, then what's coming up next would be a lot easier. But we were created with 10 fingers. So decimal is base 10. We represent that with a parentheses followed by a 10. And those are just our favorite Arabic numerals. Numerals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We know how that works so well. It's so deeply ingrained in us that we don't necessarily think anymore about what these things imply. But we're going to hop in our decibel car, or deca car, whatever, and this is the odometer of our base 10 car, and we're cruising along. 0, 0, 0, 0, 0, 1, 0, 1, 0. No, that's binary. So what's happening? Each mile we increment the ones place. 0, 0, 2, 0, 0, 3, 0, 0, 4, 0, 0, 5. We know what's going to happen. 0, 0, 6, 0, 0, 7, 0, 0, 8, 0, 0, 9. All right, I called that the ones place. In our counting system, we have places. 3 digits look kind of like this. We have a ones place. I'm going to just put a 0 out here. That is equal to 10 to the power of 0. You Python people would prefer it if I did it like that. 10 to the power of 0. And then we have another place, which is 10 to the power of 1. So 10 to the power of 0 is the ones place. 10 to the power of 1 is the tens place, and if you understand powers of, then you remember that. 10 to the power of 1 means a 1 followed by 1 0. And 10 to the power of 2 is 100, right? Followed by 2 zeros. So with our 3-digit odometer, right, we have a hundreds place, a tens place, and a ones place. So if we have a 999, that's the maximum value that our 3 digits can hold. And if you owned a car in the 70s or 80s or 90s, maybe you had the thrill of watching the odometer roll over, right, at 100,000, or wow, if it got to 1,000,000, it rolled over, right? All the 9s turned back into zeros, right? Okay, so we're counting along. We've driven past mile marker 9. Our odometer is at 9. We drive another mile. What happens? Well, we kept incrementing the ones place. We can't increment it anymore because our counting system stops at 9. It wraps back around to a 0. So we put a 0 in that place. But this would be stupid, right? Not going to do that. So what happens? We add 1 to the next place. So that 9 becomes a 10. So the ones column reset back to its lowest value, and we incremented the next one, the tens column, by 1. Okay, and say we keep cruising, and so on. Whoops, and so on. And eventually we get to, 98, 99. We go another mile. Again, we have maxed out this column. The ones column, the 10 to the power of zeros column is maxed. So it goes back to the lowest digit, rolls back over from a 9 to a 0. So we increment the next place, the tens place. Well, it's maxed out too, so it rolls back around to a 0. And then this place increases by 1. Right? And so the 10 to the power of 2's place. So we went from 99 to 100. And we know what happens when we hit 999. We go one more mile. That one rolled back over to a 0. This one rolled over to a 0. This one rolled over to 0. And now we're at overflow. Right? We only had 3 places. We didn't have 4 places. There's nowhere to store that 1. So this is overflow. And we know how that works. We were taught counting in first grade or kindergarten or something like that. We may not have remembered that this is 10 to the power of 0 and this is 10 to the power of 1, but this is 10 to the power of 2. But you did know that that's the ones place and the tens place and the hundreds, and you know what the next one is: 1,000, 10,000, 100,000, and so on. The power just keeps going up: 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, and so on. So if we have a number in base 10, it really means this. Let's say I have this number, 963. That's our number in base 10. Well, what does that really mean? Well, like I said, this is 10. This is the thousands place. This is the tens, the hundreds place. Wait, no. That's the hundreds place. That's the tens place. And that's the ones place. It's fun trying to line things up in Notepad. So we have 963 in base 10. What does that really mean? It means 9 times 100, or 10 to the 3. I'm going to write these in powers, 10 to the power of 2. That's 10 to the power of 2, as we've said. This is 10 to the power of 1, as we've said. And this last one is 10 to the power of 0. It's really okay if you don't type this in, right? Because it's kind of annoying, but if you feel like it, fine. All right, so if we have 963 in base 10, what does this mean? It means we have 9 times 10 to the power of 2, right? Because this first column is 10 to the 2, plus how many in the 10 to the power of 1 column do we have? We have 6 times 10 to the power of 1. That was supposed to be a power of there. Plus how many in the ones column do we have? 10 to the power of 0. Yeah, so 3 times 10 to the power of 0. We add all those up, guess what we get? We get 963. Yeah, we converted from base 10 to base 10. Big accomplishment. But we have to think like this in order to get to the next level, next concept, counting in binary. Right? So 9 times 10 to the 2, plus 6 times 10 to the 1, plus 3 times 10 to the 0. I wonder if there are any cultures that count in something other than base 10. Surely there are, because the Romans did not count in base 10, right? They used X's and I's and V's.
The Egyptians that do 12?
Sounds right. 12 is a good number to base your counting scheme on because it's so evenly divisible, right? You can divide it in half, it's 6. You can divide it in thirds, it's 4. You can divide it in quarters. And that's why a lot of money systems, counting systems, was based on 12, and 16 was also a good one. Pardon?
That's why we have 12 months.
Yeah, 12 months, 12 inches in a foot. All right, so binary, back to binary. As I said, we only have 2 digits. So base 2, we have 0 and 1. We're getting in our different car. We're in our binary car now. And it still has 3 places. But instead of being 10 to the 0, 10 to the 1, 10 to the 2, it's 1. Excuse me, it's 2 to the 0, 2 to the 1, and 2 to the 2. So 2 to the 0, 2 to the 1, 2 to the 2, like that. Any number to the 0 is equal to 1. 793 to the 0th power is 1. 8 billion to the 0th power is 1. And it's a short mathematical proof, but I'm not going to get up there and fumble through it. So that's a 1. Well, what's 2 to the power of 1? That just means 2. And what's 2 squared? 4. And if we had more, right, 2 to the power of 3, if we had another counting place, 2 to the power of 3 is 8. You can kind of see the scheme going on. 1, 2, 4, 8. What would the next one be?
16.
Yeah, 16 is doubling each time. Y'all get that? Okay. So those are our places. What if we had a number in binary? What if we had that number and we wanted to figure out what it was? Or what if we had this? 1, 1, 1, 1. Well, if I copy this, so that in base 2, I want to convert to base 10. I will get back to this though. Convert that to base 10. Maybe I won't. Why don't we just talk about it right now? So I have 1, 1, 1, 1. I'm going to copy this stuff and paste it so that I can put my 1, 1, 1 underneath it. That's a 1. That's a 1. That's a 1. And that's a 1. What is this? This is 1 times 2 to the 3. Or 8, right? Plus 1 times 2 to the squared. Plus 1 times 2 to the 1. Plus, and it gets tedious typing these 2 to the powers of, right? Plus 1 times 2 to the power of 0. You'd be totally forgiven, and I would encourage you to do it like this. 1 times 8, right, plus 1 times 4, plus 1 times 2, plus 1 times 1. Or you could even just go, well, I have an 8, right? I have a 4. I have a 2. And I have a 1, right? All of those are lit up. All of those are on. So we have all of those numbers in it. And if we add them up, 8 plus a 4 plus a 2 plus a 1 is 15. Yeah. So that means that 1, 1, 1, 1 in base 2 is equal to 15 in base 10. I'm going to throw up another number on there, and we're going to convert it the same way, but I'm not going to write it 3 different times, right, like I did here. I'll probably just pick that way. All right, so I'm going to copy this stuff again, but I'm going to pick a different number. Maybe 0, 1, 1, 0. Okay, so convert 0, 1, 1, 0. Base 2 to base 10. So it's 0, 1, 1, 0. Put a 0 there, a 1 there, and a 1 there, and a 0. All right, how many do we have in the 8's column? Deafening silence. Come on.
6 to the power of 10.
Wait.
I mean 6
No.
base 10.
How many
There's 0.
do we have in the 8's column?
0.
We've got 0. Right. So 0 times 8 plus how many do we have in the 4's column?
1.
Yep. Plus 1 times 4 plus how many in the 2's column?
1.
And then how many in the 1's column? None. Right? That makes sense? And sometimes people's brain glitches on that. I understand that. If you're still having trouble with it, I can find a YouTube video on it that'll help you visualize it better than I can explain it. It's okay if you don't get it first time. I do want you to get it though. Okay, and so we don't have any 8s, but we have a 4 and we have a 2. So 4 plus 2 is equal to 6 in base 10. Now I'm going to show y'all how to convert the opposite, how to go back from decimal to binary, but I'm not going to show you the numbers. I'm going to show y'all that it's possible. So here's how I would have done it before I learned this algorithm. I would have gotten a number, like say 13, and I would have said, well, how many 8s could I fit in there? I can fit in 1. And 13 minus 8 gives me 5 left. How many 4s can I fit in 5? 1. And then that would give me 1 left. How many 2s can I fit in 1?
0.
0. And then how many 1s can fit in, right? And so I did that. That's how I did it until I learned this algorithm. That makes sense to me. But if you're dealing with a really long number, like, you know, if you're dealing with 234, it's a drag to do it. How many 256s have we got? How many 128s? How many 64s? How many 30, right? So.
That's when you just Google a calculator.
Yeah, you grab your calculator. Exactly. But say we have the number 241 in base 10, and we want to convert it to base 2. What you start doing is you start dividing. 241 divided by 2 is 120 with a remainder of 1. This is the important column. Now we take that 120 and we divide it by 2 and we get 60 with a remainder of 0. 60 divided by 2 is 30 with a remainder of 0. 30 divided by 2 is 15 with a remainder of 0. At least now we have an odd one, right? 15 divided by 2 is 7 with a remainder of 1. 7 divided by 2 is 3 with a remainder of 1. 3 divided by 2 is 1 with a remainder of 1. And then 1 divided by 2 is 0 with a remainder of 1, and we're done. We don't have any more division to do. Now this is actually our answer, but you start writing it down from the bottom up. 1, 1, 1, 1, 0, 0, 0, 1. And we could enter that into a calculator or something. We would find out that that is equal to 241. We could figure it out ourselves if we wanted to, if we knew the places. This first one is a 256, just because this is equal to 2 to the power of 7, and 2 to the power of 7 is equal to 256. So the next one is a 128, and so on. So we have a 256, we have a 128, we have a 64. Notice I'm dividing by 2 each time. We have a 32, and we have a 1. So if we added 256 plus 128 plus 64 plus 32, and then the final one, just take it on faith, we get 241. Hope so. Am I going to ask you to do that? Nah, I just wanted you to see it. Now we've seen kind of the front and the back of it, right? People watching at home didn't get to see any of it. Hope that was fun. All right. So we're in our odometer. We hop in our binary car. Been waiting for this since the very beginning of the class. We go and drive a mile. This is binary counting. All right, we drive another mile. Error, does not compute. Why is that bad? We don't have any 2s in our counting system, right? Binary counting is all 0s and 1s. So we can't hit 2. That rolls back over to the minimum value, and we increment the next field. Then we go another mile. And this is just like when we were at 99 and it rolls over to 100. We want to go another mile. We need to add 1 to that. Whoops, we've maxed out. So set it to the minimum. Well, add and carry, huh? Or carry and add, whatever. That one needs to be incremented. It can't go any larger. Then we increment the next one. There's only 8 possibilities for these 3 bits, for reasons why we'll see in a minute. So I don't have to go much farther. This looks repetitive because it is. What's our next mile? What's the numbers, the bits for it?
101.
Yep, 101. And what's the one after that?
110. And 111.
And 111. Okay, and if we count them out, counting as 0, right? We don't have any 4s, we don't have any 2s, we don't have any 1s, so that's equal to 0. Here we have a 4, and we have a 2, and we have a 1, so that's equal to 7. 4 plus 2 plus 1. And if we count, yeah, there are 8 different possibilities going, right, from 0 up to 7. That gives us 8 different possibilities. And if we drove another mile, it rolls over, overflow. It's too large to hold in that space.
So, can you only go up to 7?
If we have 3 bits. Our computers nowadays got standardized sometime in the 60s or the 70s or something like that, so that there were 8 bits in a byte. So if we want to go up to 7, and we wanted to know how many different possibilities there are, there happens to be a formula for it. 2 to the power of 3 is equal to 8. We have 3 bits. 3 bits can hold 8 different possibilities from 0 up to 7. Well, what if we had 8 bits? Your Nintendo was an 8-bit computer. Well, 2 to the power of 8, I'm not going to make you calculate it because I happen to have it memorized. 8 bits can hold 256 values from 0 up to 255. And we could prove that, right, by writing out the 8 places. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. Okay, those are our 8 place values. It doubles each time, right? And if we added all those up, you know, 1, 1, 1, 1, 1, 1, 1, 1, and base 2, we added all those up, that equals 255. The largest value you can store in 8 bits. 255 in base 10. Alrighty, I want to upload this worksheet and we're going to play with it together. Let's see if we've got enough of it in place to go. Yeah, I think we do. No, we got to go further. A drag. Well, we can do at least the very first part. Then we'll keep lecturing. I'm going to actually call this homework 5 even though we're doing it in class. Just because. Get a free homework grade out of it, right? Binary and a hex worksheet. We haven't talked about hex yet. That's short for hexadecimal. We certainly will in just a moment.
Should we do it on notepad then?
Now I'm going to give you the worksheet. Just a sec. You can download the worksheet and work on it from there. It makes it real easy. That's the only reason why. growing disenchanted with the auto hiding of the taskbar. There we go.
Didn't you say we were gonna have quizzes?
The quizzes, I think we're still stuck on chapter 2, so really we haven't hit very many quizzes yet. But they're over in the quizzes tab.
We have exams too.
At a certain point.
In 7 days we have exams?
No, I don't know why that came up.
It said the 28th.
We're going to just kind of hide the exam for now.
Okay. That's good.
But I need to set a due date for it soon.
Yeah.
But the first one's going to be over chapters 1, 2, and 3, and we're still plowing our way through.
Could you make
Chapter
me
2.
do on a Friday? So I don't have to go to work.
Yeah, I'll make it due Friday, but we're going to take it on Thursday.
Oh.
But you can skip Thursday and then take it at the library Friday if that's how you want to do it. So technically it'll be due Friday.
I don't care if
It's
you take
due
it
Friday. You
fast,
can
right?
try and take it Thursday, but it's due Friday.
Right, it's-
For your bosses.
Right.
Can you make it do like a quarter?
6. We'll make it do a 6.
Can I have 100?
Much better.
Yeah. Yeah, while we're giving this stuff out. All right, let me upload that now. Come back. We're about to start the worksheet, the most exciting part of the day.
I've got mine. Come back here.
Really though, if you need to miss the day, this isn't for, for everybody. If you can't be here on a day, I'll leave the exam open, so that you can take it over the weekend or on the following Monday.
Make it do on weekends.
I'm sorry, boss. I need to work on my exam 5 days in a row.
Every day.
5 minutes, yeah. All right. So it's there now. So refresh your assignments folder. Go down to homework 5. Click on the document. And here we go. So fill in the yellow blanks on the next 2 pages. All right. But we're going to give some examples first. Convert this number to decimal. Well, we already have the places filled out. The 1's place, the 2's place, the 4's place, the 8's place, and the 16's place. And so 11010 is equal to 16, because there's a 1 there, plus 8, because there's a 1 there. But there's no 4's, right? So I'm not going to add a plus 4. But there is a 2, and there's no 1's. So 16 plus 8 plus 2 is equal to 26. So here's an example, or here's one for us to do. 10101. What's our first number that we're adding if we're going left to right?
16.
Yeah, we have a 16. Do we have any 8's?
No.
Everybody see why we don't have any 8's? I absolutely want to make sure you see that.
Zero.
Right, because of the 0. Right, so we don't have any 8's. How many 4's do we have? 1. So that's a 4. How many 2's? Zip. And how many 1's? Okay. Now, honestly, if you get this far, I don't care if you do the math right. Right? This is the important part. If I ask this on an exam and you only go that far, you get full credit for it. Because, if you're adding this stuff in your head and you're like me, you may get it wrong. Now, I think I could do those 3 numbers and get 21 and hope that it's right. But all right, we've got more to do, though. And I want you all to do these. The first one's done for you. I'm going to erase it and redo it as a demonstration, and then I'm going to let you all do it. What is this place? What is the last place? Well, this one's a 1, so that makes that a 2. That makes that a 4. That makes that an 8. That makes this one a 16. But we don't have any 16s. The first one we have is a what? No 16, so what's the next one over?
8.
right? So it's an 8. Do we have any 4s? But we have a 2 and we have a 1. And if we add those up correctly, I believe it's 11. If you feel like doing this awesome little base 10 thing after it, that makes me happy to see. All right, I'd like for y'all to do those 4. I'll do them up here afterwards, but I want you to take a stab at it. Does it look like editing a Word document?
Well, this isn't actually the word doc. I took a picture to
Picture of
import
it. Okay.
Yeah.
Cool.
Does it matter which order we have to read?
You could go left to right or right to left. Yeah, if you don't know what the last number is, right, you could start the other way. I have a 1, no 2s. I have some 4s, and I have some 8s. Doesn't matter whether you go from small to large or large to small.
Is that okay? No, it's not. Is that all we're doing?
Well, we're going to do more today. We're not going home yet. All right.
No, like on this sheet.
Right, right. And then there's something coming up that we're going to talk about on the next sheet.
So then.
So don't submit it yet. All right. Okay, so this one has a 16. So it's a 16 plus a, does it have any 8s? We're looking at this row. No 8s. Does it have any 4s?
Yeah.
one.
And a 2.
And a 2, but no 1s. So that's a 22. All right, I'm going to make you do this on the board if you don't stop talking. All right, how about this one? Well, I'm going to flip this one up and I'm going to start counting the other way. There's a 1. Are there any 2s?
No.
No, but there is a 4 and an 8. Which is a 13 in base 10. All right, how about this one? It's got 3 numbers in it. What are those 3 numbers?
1, 2, and 4.
Right, 1, 2, and 4. Everybody get that? I'm starting at the smallest now because it's easy in my head to start with 1. But it could go either way, right? There's no 16s, there's no 8s, but there's a 4, there's a 2, and a 1. So 4 plus 2 plus 1, or 1 plus 2 plus 4, however you like it, is 7. And lastly, all 1s. That's a 1 plus 2 plus 4 plus 8 plus 16. Or 16 plus, right. 16 plus 8 plus 4 plus 2 plus 1 is equal to 31 if I'm not mistaken. All right. And like I said, I don't care if you add it correctly, if you wrote 32 there or whatever. As long as I see that, I know that you know the concept. All right, the next, hexadecimal and binary. Hex is a counting system that has 16 digits. It's got more than 10 digits, which our counting system has. What? Go away. All right. That hex meaning 6, like a 6-sided sign, and decimal meaning 10. 6 plus 10 is 16. So the hexadec, if I could type, hexadecimal, I still have the recorder going, yep, is base 16, is like that. And I'll show you the and somebody later. So it's got 16 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Uh-oh, ran out of digits. Well, we just got to pick 6 more to get up to 16. Why not pick the letters? It didn't have to be those letters. It could have been, W, Q, R, S, T, U, V, W, X, Y, and Z. You can bet that the Russians, when counting in hexadecimal, did not count, in A, B, C, D, E, and F because they have their own letter system. Now, of course, everybody uses the same, right? Kind of standardized worldwide. And it always amuses me or interests me to think that, everybody is learning English of some sort when they learn how to program in these languages. Okay, so we have 16 digits. So if we hop into our hexadecimal car, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. Have we maxed out? Do we have to roll over yet?
Nope.
We do not roll over yet because we're only this far. We have 6 more miles to go. So 0A, 0B, 0C, 0D, 0E, and 0F. Now we have maxed it out. We've hit the last digit. So at this point, this is the point where it's going to roll over. And we're going to get a 0 in that column, and we're going to add 1 to that column. And so let's just keep pretending that we've driven a long way, and we're now at mile number, and this looks silly, I know. We're now at mile number A7. What's after A7? Add 1 to 7. It's A8. What's next?
A9.
A9. What's next?
A.
A, not B, but very, very close. The 9 becomes an A when we add 1 to it. Then AB, AC, AD, AE, AF. F is the max. Now it rolls over and it becomes B0. The F rolls over to become a 0, and we add 1 to the next column. And we eventually get to the point where we're at FF, and we want to add 1 to it. Well, F turns into a 0. So we add 1 to the next column. That becomes a 0. Boom, we've hit an error. We've hit overflow error. Hope that made sense. So the next thing we need to talk about are the powers again. Instead of 2 to the 0, 2 to the 1, 2 to the 2, or 10 to the 0, 10 to the 1, and 10 to the 2, we have powers of 16. We have 16 to the power of 0. Anything to the power of 0 is 1. 16 to the power of 1. Anything to the power of 1 is itself. 16 to the power of 2. That's 16 squared. And 16 to the power of 3. We have 4 places if we're talking about 4 digits. You could keep going, right? So that's the 1's place. This is the 16's place. This is the 256 place. And honestly, I don't remember what 16 to the power of 3 is, so I'm going to ask Google. 16 to the power of 3, 4096. So there we go. Say we have the number 01A7, and we want to convert that to digital. 01A7 in base 16 to decimal to base 10. Question mark, base 10. Well, I'm just going to line up 01A7 underneath these numbers. I'm going to copy those numbers, pretend to fill in a little table. 0, 1, 8, 7. Alrighty, how many 4096s do we have? We don't have any, right? Because you see 0 in that place. We don't have any 4096s. So 0 times 4096. How many 256s do we have?
Wait, why do you put 8 instead of 8?
Which part is the question?
Why do you put an 8 instead of an 8?
Because it goes.
Good, but good question, because I had a brain fart. It stunk. There we go. How about that? Thank you. Alrighty, so we don't have any 496s. How many 256s do we have? We have 1. 1 times 256 plus how many 16s do we have? Well, we need to remember what A is.
9 of 10.
If we look up here when we were counting, it is equal to a 10, right? Because an A is a 10, a B is an 11, a C is a 12, 13, 14, 15, like that. Let me space it out so that it's clear. Okay, so an A is a 10. Anytime I give you problems about converting hexadecimal, I'll give you this chart and another one that I'll show you, because I don't want to make you take the time to either think, well, what's a D? I don't remember what a D, you know. Okay, so we have 10 times 16 plus, let's make this one even more awesome. Let's make this an F. And what did we say an F was?
16.
Close.
15.
15. So 15 times 1. And we could do all this math, or I could just copy and paste it into Google because I'm extraordinarily lazy. That's equal to 431, if Google is correct. I could give you more problems like that, but I hope that demonstrates it. We've done the other ones enough that you could get the idea. But let's see if there were any in the worksheet like that. So let's flip back to the worksheet. I see notes being taken. That's why I'm not covering the screen up yet.
Got it.
Okay. All right, here we go. Hexadecimals, base 10. Not only do we have 0 through 9, we have these extra letters, these extra digits, which mean 10 through 15. And we have our powers of 16. 16 to the power of 0, 1, 2, and 3. So we're going to convert 12AF to decimal. 12AF. That means how many 4096s do we have? We have 1 4096. How many 256s do we have? 2. How many 16s do we have? I seem to like putting A in that spot. 10 times 16 and 15 times 1.
Why is there a parenthesis 2?
Pardon?
Why is there a base 2 and a half?
Because I goofed horribly. I brought shame to my ancestors. Who wants to slap my wrist?
And
All right, all right.
knuckle back.
All right, so that should have been a... You are awesome. You're a good copy editor. All right, make these 16s. Whee! All right, thank you. And wow, I thought there was a third page of this, or one more section, and I don't see it.
Let's see, what's that last one? That's the last of what?
Last of 3 pages. Yeah. All right, how about this one? Do it yourself. And then I'll wander around. And Sorry, gang, watching at home. I went ahead and answered it. But you can do it by yourself as well.
Wait, is it base 16 or base 10?
Base
We just
Base
converted
16.
it into base.
We converted base
Oh, we converted
16 to decimal, to base 10. And so the weird thing, not that it's that weird, but if you're given a number like 1, 2, 3, you really don't know what that equals. You have to know the base in order to know what it is, right? Is that base 10? Is it base 16? Its value is dramatically different depending upon whether it's base 10 or base 16. If it's base 10, right, 1, 2, 3 is equal to 1, 2, 3. Just kind of a tautology or something there. But if it's 1, 2, 3 and base 16, that means it's 1 times 256 plus 2 times 16 plus 3, whatever that is. $291. Right, in base 10. And it's kind of deceptive. If you have also, if you have A's and F's and stuff in it, you know pretty much it's hexadecimal. But if there aren't any, then you have to figure out whether it's base 10 or base 16. I could ask you, what is 1,000 in base 10? Assuming that you knew that I meant from base 16, but I shouldn't assume that. I better tell you, right?
So then how do we do base 10 to base 2?
Base 10 to base 2, that was when I got up there and I did that division. I could show you again, but I don't want you to know. No, I'm kidding. Do you want another example of it? It's okay to say yeah.
No.
Okay. You divide by 2 and carry. And it's the column of remainders that we did. I took 241 and I kept dividing it by 2, and then I started here and I wrote my number from the bottom up that way.
That's 10 to 2, right?
Yeah, that's base 10 to base 2. What if we want to convert base 16 to base 2? I'm not going to make us convert from base 10 to base 16. My mind breaks there. I'd whip out some calculator or something to do that. In order to hold values up to 15, we need 4 bits. Okay, those are the powers, excuse me, those are 0 through 7 in base 10. So this is base 2, that one, this is base 10, and we have one more column, base 16. Those are just the same at this point, right? There's nothing unusual about the digits 0 through 7. I ought to be using tab. It would make it easier to type this. All right, but we didn't max out our bits, right? 3 bits goes up to 7 because 2 to the power of 3 is 8, so 8 minus 1 is 7. But we're going to keep going. 1,000, 1,001, 1,010, 1,011, 1,100. What's next?
1101.
Yep,
111.
1110, and lastly 1111. So just counting, not even figuring out 2 to the power of whatever. That's an 8, right, because this was a 7. That's a 9. That's a 10. That's an 11, a 12, a 13, and a 14, and a 15. Which is equal to, so again, this is base 2. Come back, this is fun. This is base 10. This is base 16. So again, nothing unusual about 8s, nothing unusual about 9s, but here's where they start going into letters. 10 is an A. And when you get caps lock accidentally stuck, then it's annoying. All right. There we go. Now, why did I show you that? Because we can convert directly from hexadecimal to binary just with this table. To prove it, I'm going to come up here and I'm going to find, no, it's not going to prove it. We don't have any examples yet. I'm going to take this number, let's convert the number 2 for FB in base 16 to base 2. And we're not going to mess with powers of 2 at all. We're just going to look up, right? So here's a 2. A 2 in base 16 is a 0, 1, 0, 0. I'm going to put spaces just to break this up visually because otherwise it's hard for me to see. So what's a 4? A 4 is at 0100. And yeah, we could add it up, right, to make sure that it's true. Okay, wait, I've already messed up. What really is a 2? I typed that in wrong. 0, 0, 1, 0, and then what's a 4? 0, 1, 0, 0. And so what's an F? An F is all ones. And then lastly, a B is what? 1011. So 2, 4, F, B is equal to that. So 8 bits, excuse me, 4 bits. Each one of these is a chunk of 4 bits. Now we said that a byte is 8 bits. So that's 8 bits. And then another 8 bits. So far this is a 16-bit number. Like you had a 16-bit computer like your Super Nintendo or your Genesis, you know, back in the early 90s. We could have more bits. We could have 32-bit computers. Ints are 32 bits. So if we had that, we might have this number. 2, 1, 7, 3, A, B, 0, 1. Just making it up. All right. So somebody tell me what a 2 is. You can look it up.
0, 0, 1.
Yep, 0, 0, 1, 0. What's a 1?
0, 0, 0.
A 7?
1, 1, 1. 0, 0,
Wait, slow down. I can't type that fast. Hey, this is the first time that y'all have been going faster than me. That's awesome. All right, so that's a 0, 0, 1, 1. What's a 10? 1, 0, 1, 0. Because you see that one. You're tired of speaking aloud, but I would appreciate it. Okay, what's a B? 1, 0, 1, 1. What's a O? A 0. Zeros. And then a 1 is 0, 0, 0, 1. Okay. So that's what this looks like underneath it all. Inside our computer, if we have a 32-bit number, it looks like that. And if we wanted to display it in hexadecimal, that's what it would equal. Then the question becomes, well, why would you display that in hexadecimal? Why not just display it in decimal? I don't know if I'm going to answer that right now. Yeah, the answer is that if you do this in decimal, each number takes 2 spaces to hold. Right, because what's a 2? A 2 in base 10 is a 2. What's a 4? It's a 4, but what is a F? It's a 15. And what's a B? It's an 11. So we really have to have 2 digits, right, in order to display these 16 bits as decimal numbers. But it only took 4 digits to display it as hexadecimal numbers. So since these are cleanly convertible to each other and you could display twice as much data on the screen at the same time, it was useful for computer scientists to be able to put, you had an 80-column screen, you could put more numbers on, right, more letters on. You could put twice as many hexadecimal digits on the screen as you could do that. And you could look at it, and once you've looked at this long enough, if you've been doing this for months and years, you know that an FB is going to be that, right? You could just rattle it off. You could spot it and vice versa. So it was useful for them to develop hexadecimal. We don't care that much. Well, then why are you talking about it? Because you may hit it as a programmer. And you need to know how to do that. Now there's another way of representing hexadecimal other than that base 16. I'm going to delete this line because that one was a little bit confusing comparatively. But I am curious about this. You see that number right there? What is that equal to in decimal? Well, I'm sure not going to add it up. Again, I'm going to let my dear friend Google do it for me. I'm going to type this in. Like that. I'm going to show you how the languages refer to hexadecimal digits. If the number starts with 0x, that means it's a hexadecimal number. And that equals this number, 5 billion, or 500 million. I'm just going to copy this and space it out. You don't have to type that, but I'm just trying to show you. Okay, so if your computer has a number 561,228,545, then somewhere in its memory it's got this series of bits and bytes, series of zeros and ones. How does it hold negative numbers? To hold negative numbers, you have to kind of flip your thinking around. They say that the first bit does not represent an 8, but that the first bit says that it's a negative number. So 1001 you could treat like it was a negative 1, right? This means, oh, I'm a negative, and then that's a 1. 1010, that means that's a negative 2. 1011, that's a negative 3. Now somebody in the back is a computer engineer and knows that I'm lying through my teeth. Now this is a 1100, so that's a negative 4. That's a negative 5. That's a negative 6. And that's a negative 7. That's called 1's complement, by the way, when you take those numbers and you make them negative like that. Now the reason I said I'm lying through my teeth is because what is this? If that's a negative sign, what do all those zeros add up to?
0.
Yeah, and is negative 0
No.
a something that we should think about? No, it's not. So what they do is they shift it all up by 1, where this is negative 1, this is negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. So if you have to have a sign bit, then you cut in half your largest value, but you can also have small values, right? Negative values. Negative 1 to negative 8. Don't care too much about that, but if you hear about the sign bit, it means that the first bit dictates whether it's positive or negative. And we will see that when we get data overflow. Data overflow is when it exceeds, when the number gets so large that that bit gets flipped. And if that bit got flipped, no longer, it's going to be some kind of negative number. Don't know what it is, but it's going to be a very large negative number, right? We would have to convert all of this to a number, and then we would say, okay, minus, because this is effectively the minus sign, where 0 is a plus and a 1 is a minus. You know, we could do it. It wouldn't take too long.
This A and B are the only ones negative then.
Yeah. Okay, so actually, if this was a negative, it would be a negative 2. Right, so it would look the same. It would just be negative of the whole thing plus 1 more, 561. And I'm going to erase this because it kind of makes no sense. But 546. Okay, so if we stuck a 1 here instead, it equals that. Just tuck it away in your head that if a number gets too large, then this bit becomes set to 1, and suddenly the number becomes negative.
So you only on the very first initial digit
Right,
dictates it?
right. Whether it's an 8-bit number or a 4-bit number or 16 or 32 or whatever. That's why we have the uint, the unsigned int data type. It's a 32-bit number, but we only get to use 31 bits, and the first one is that sign bit. And are we out of time?
6 minutes.
We've got 6 whole minutes. Let's write a program that demonstrates the sign bit clicking over. You already have the worksheet, and you can upload it into the homework box. That's going to serve as our Dropbox for today. So empty project. Y'all don't have to do this. You can just watch me do it.
You say we don't have to do it?
Nah,
Why?
because we've already done the worksheet. All right, so I'm going to start a number counting, and I'm going to add like 100 or 1,000 or 10,000 or 100,000 to it each time. So int number is equal to whatever. I'm going to start it off at 1 billion, which is a 1 followed by 9 zeros. Large number. All right, and then we're going to have a loop. It's going to go forever while true, but I'm going to put a break in it so it stops at a certain point. So let's print out the num, cout num, and then let's add 10,000 to it or 100,000 to it. So num plus equals, there, like that.
That's 100,000.
Yeah, I'm adding 100,000 to it. I'm going to add 100,000 to it. I'm going to print it out. But then if it's too large, it's flipped over and gone negative. So if num is less than 0, it means overflow has occurred. It's gotten too large, and we're going to break out of our loop. All right, we see it counting. Eventually, it's going to exceed the largest value that can be held in a 32-bit int. Now, if we made it a long, it would take forever. Okay, you see that? We went from that, we added 100,000 to it, and all of a sudden, we have garbage data, right? We exceeded the maximum value of it. And the reason that it went negative is because of that sign bit. If we took this number and we added 100,000 to it, and we wrote it out in bits, we'd see that all of a sudden that first bit is now a 1 rather than a 0. All right. I think that's about enough of bits and bytes. The last thing I would have mentioned if I'd given ourselves time, and rather than do that, is you could go vice versa. You could take these bits and swap them back to bytes, right? So if I had this, okay, so what is a 0101 according to our lookup table? What letter is it, or what hex digit is it? That's a 5, and then what's next? That's an F. And what's that one? That's a 0. And what's that one? 1101
D.
is a D. Okay. So this in binary is equal to this in hex. Real easy to do these conversions if you have this table. I'll probably give you a homework assignment or something. I'm going to give you that table to make it real easy. You saw how easy it was. You just went from that column to that column, or that column to that column. And let's call ourselves done. Go ahead and upload the worksheet, assuming you filled it out. If you didn't, upload an empty worksheet, but I think everybody did. And that'll be our homework.
I have a question, but it doesn't really pertain to the class that much.
Oh, yeah?
I was wondering if you have any Cisco certs.
I do not. I do not have a one.
So I'm just trying to find more people who have done the CCNA.
Yeah.
Could you minimize so I can see your program?
Yeah, sure. Sorry. Uh-huh.
Oh, look at this guy.
Yeah.
Also, did you put a certain number of, 10000, did you put some number for specific reason, or is it just?
I just wanted to start it large at 1 billion because I knew it would roll over at about 2 billion.
Right, so this is always roll over and double. what's put in there?
No, if you change it to 0 and let it run, it just takes longer to get there, but it'll still roll over at 2 billion. This is just a random starting point. If we made this,
So it randomly started at like 100 million?
well, when I say random, yeah, I chose 1 billion, but now I'm going to make it larger. It's still going to do it. It's just going to reach it more quickly now.
Does it know it'll double it each time?
I'm not doubling it each time. I'm adding 100,000 to it each time.
Oh.
You could double it to reach it real fast, right? If you were doubling it each time, it'd go negative, right, just after 32 doublings.
Got it, I understand the program.
Okay.
Oh.
Uh-huh.
So, am I going to
This is free license, free trial. You're going to want to actually register it. I don't remember how you register it. Go to help. Register product. Create an account. It's probably going to ask for, an email address. You can just give it. So we'll find out.
my Hotmail one?
Whichever one you want. Hotmail's a great one. So that's owned by Microsoft. Oh, already a Microsoft account.
So make a new one or use a current one? Use your
Go back and like use your Rose email address.
address, yeah.
Yeah, so use your email instead. I saw 2 variables. We changed it to add. Just say
What the
five.
heck?
Well, you see how I did that?
Yeah.
Okay.
Do what? Homework.
No, it's conversion. The worksheet one is the homework.
Yeah.
Sign in.
They don't want to make one.
Try your Hotmail address.
Oh,
Because
yeah,
you know
that
your
would be to do
password.
my password.
It'll ask you for your password, but you know your Hotmail password, right? No.
I have
Okay.
it written somewhere.
You might just have to create a new email address through them.
I'm having trouble because I can't remember my Apple ID,
Right.
and it's not letting me do anything.
That'd be an important one to figure out how to recover.
Yeah, I think somebody said I could go up to the Apple store, but they don't even, you can't just go in there. You have to make an appointment, and I don't know when I can get in there.
Right. So have you done this? Have you gone to, oh, let me stop the recording.
I tried even starting a new one, and because my email, I've used it on 2 or 3 Apple
Right.
accounts, it won't let me do it.